Good morning all. Let us discuss a problem using Ampere's law. Find the magnetic field of a very long solenoid consists of n closely wound turns per unit length carrying a steady current I. The solenoid consists of n closely wound turns per unit length. The current passing through the solenoid is I. Here the direction of the current is circumferential. The direction of the current is circumferential. Therefore, the magnetic field inside the solenoid runs parallel to the axis. It is from the right hand rule. Here the current runs circumferential. Therefore, the magnetic field runs parallel to the axis. And from right hand rule, we can say that B points upwards inside the solenoid and the value of B is 0 outside. Now to find the magnetic field of the solenoid, draw an Amperean loop as shown in the figure. Draw an Amperean loop as shown in the figure. Now here it is a rectangular loop ABCD with the length of the loop is L. The Amperean loop is drawn in such a way that it is partially inside and partially outside. If you consider a rectangular Amperean loop ABCD, then by Ampere's theorem, closed integral B dot dl, that is equal to mu 0 I enclosed, where I enclosed is the current enclosed by the Amperean loop. Now how do you find closed integral B dot dl? Consider a rectangular Amperean loop ABCD and we have to evaluate closed integral B dot dl, and that is equal to mu 0 times the current enclosed by the Amperean loop. Closed integral B dot dl can be represented as integral a to b B dot dl plus integral b to c B dot dl plus integral c to d B dot dl plus integral d to a B dot dl. Closed integral B dot dl can be written as integral a to b B dot dl plus integral b to c B dot dl plus integral c to d B dot dl plus integral d to a B dot dl. If you evaluate the four integrals separately and add together, then you will get closed integral B dot dl. Now let us evaluate each integral separately. First, closed integral a to b B dot dl. What is dl? dl is a small element of length along AB, and the direction of the field and the direction of dl are same. So integral B dot dl becomes b dl cos 0. Since the field is constant, you can take it outside. So b into integral a to b dl. Now integral a to b dl is nothing but the length of the Amperean loop. So integral a to b B dot dl becomes b into L. Now let us evaluate integral b to c B dot dl, where dl is the elemental distance along BC. We can see that along BC, the magnetic field is perpendicular to dl. Therefore, B dot dl becomes b dl cos 90, that will become 0. Now let us evaluate integral c to d B dot dl, that is integral c to d b dl cos 0. Why it is cos 0? Because dl and b are parallel. That is b into integral c to d dl. Now CD the segment CD lies outside the solenoid, and outside the solenoid the magnetic field is 0. Therefore, integral C to D B dot dl becomes 0. And finally, we have integral D to A B dot dl. Now, along the path dA, consider an elemental distance dl which is perpendicular to the field. Therefore, integral D to A B dot dl is B dl cos 90, and that is 0. Now, adding the evaluated integrals, we will get closed integral B dot dl. Hence, closed integral B dot dl becomes BL plus 0 plus 0 plus 0, that is BL. Closed integral B dot dl equal to BL. Put it as equation number 1. Now, from Ampere's law, closed integral B dot dl, which is nothing but mu 0 I enclosed, where I enclosed is the current enclosed by the Amperian loop ABCD. How do you find the enclosed current? Now, inside the Amperian loop, there are several turns, and since the current passing through each turn is I, now we can say that each turn will contribute a current I to the Amperian loop. That is, in the present problem, I is the current passing through each turns. I is the current passing through each turns. Therefore, each turn will contribute a current I to the Amperian loop. Let us take L as the length of the solenoid in the Amperian loop, because the solenoid contains n closely wound turns together. Let L be the length of the solenoid in the Amperian loop. Since the turns are so closer, we can say the length of the Amperian loop is nothing but the length of the solenoid inside the Amperian loop. And let n be the number of turns per meter. Let small n be the number of turns per meter. And current passing through each turn is I. Then we can write the enclosed current I is NIL. NIL. Now we have closed integral B dot dl is BL, that is equal to mu 0 I enclosed. Let it be equation number 3. And I enclosed equal to NIL. Let it be equation number 4. And from 3 and 4, you can have BL, that is equal to mu 0 NIL, or B is equal to mu 0 NI. B is equal to mu 0 NI is the magnetic field due to the solenoid, which runs parallel to the axis, and 0 outside. That is, B is equal to mu 0 NI Z, where Z is the direction. B is equal to mu 0 and NI Z cap inside the solenoid, and B is equal to 0 outside.